So for number 17, we are taking the area bounded between these two curves and then rotating about the line x is equal to 3. So I've drawn our curves x is equal to 1 minus y squared here, and then I've also drawn x is equal to y squared. And we can see that the area bounded between them is this little section here. So we are going to rotate this about this axis, right? Not axis rather, but this line, x is equal to 3. And so when we rotate it, what is going to happen is we're going to have this, maybe I should do it in a different color. Let's do it light blue. We're going to have this disc that goes like this. It touches the outermost part, it touches the orange curve, and then the innermost part will touch the blue line. Sorry, the green line, the light green, yeah. And it will go something like this. And so we're going to have a bunch of these discs stacked up across the y-axis, and then when we stack a bunch of these discs, it's going to give us a volume, right? In the same way that if we stack up a bunch of coins, it gives us a cylinder that has a volume. So our job here is to find an expression for this disc so that we can integrate it, because integrating is to sum, right? And so this disc here is, we're going to get it by taking the outermost area, right? So maybe I'm going to color that in, taking this outermost area, and then removing from it, a smaller part of it. So when we remove a small part of it, we're just going to be left with the outer ring, which is what we want. So to get this, we actually we have the bigger circle, right, that goes R1 minus the smaller circle that has radius R2. So the ring is equal to A1 minus A2, or pi R1 squared minus pi R2 squared. So we do have to find R1, and as we could see here, R1 is just the distance from the line x is equal to 3 all the way out to the orange line, right, which gives us our outermost radius. So how do we calculate this? Well, this distance here, I'll put it smaller, this distance here is just this whole thing, 3, minus this little section, right? Actually, this was a terrible drawing. Maybe I'll redo this. It's just this part minus this part. So if we go 3 minus the length of the orange, it's going to just take us from here all the way out like so. And this gives us our R1, right? So we do have an expression for this. This is, so A1 is equal to pi. And now this radius is just 3 minus that orange line. So 3 minus y squared. And similarly, A2 is equal to pi. And now we're going to repeat the same procedure. We're going to go 3 minus this part here. So it'll take us from the center all the way out to the green curve. And as we can see, that is the smallest part of the radius, right? So for this one, we're going to have 3 minus the green curve. So 3 minus 1, and then minus y squared, so plus y squared, which is equal to pi times, and that's 2 plus y squared. And I forgot to put the square here because it's r squared. So let's FOIL this out and expand it. So we have pi, and then when we FOIL this, we're going to have y to the power of 4 minus 6y, and then plus 9. And for the other one, we're going to have, which is equal to pi, once more y fourth, and then plus 4y, and then plus 4, yeah. So when we go a1 minus a2, we still get the pi outside, but now we're going to go y to the power 4 minus y to the power 4. They're going to cancel, and then minus 6y, that should have been y squared. Minus 6y squared, and then minus 4y squared, so that gives us 10y squared, and then plus 9 minus 4, so plus 5. And so now we have the expression for our integral, right? We're just missing the boundaries of integration. So the boundaries of integration go from here to here. So to find these boundaries, it's where these curves intersect. So we're going to set them equal to each other. We're going to go 1 minus y squared is equal to y squared. So we'll bring the y squared to the other side. Therefore, 1 is equal to 2y squared. So 1/2 is equal to y squared. And therefore, y is equal to plus or minus 1 over root 2. I just took the square root of both sides. So when I'm setting up my integral, instead of going from minus 1 over root 2 to plus 1 over root 2, I'm going to see that there's symmetry, right? Because the parabolas are symmetric, they have a line of symmetry. So it's the same thing if I were to sum up these discs all the way from down here to up here, or to say twice the sum from 0 all the way to up here. It works out the same. So we're going to do that just because it makes our integration easier. 1 over root 2, and now we're going to integrate. Remember that we're integrating a1 minus a2, so we're integrating this guy over here. Now the pi is a constant, so I'm going to put it outside, and this gives us minus 10y squared plus 5, and then times dy, because we're stacking these discs vertically. So now we're ready to integrate. This is just 2 pi that goes outside, and then times minus 10y cubed over 3 plus 5y, evaluated from 0 to 1 over root 2. So when we plug in this upper boundary, it's going to give us 2 pi, and that gives us, let's see, 1 over root 2 cubed, that will give us minus 10 over, let's see, that gives us 2 root 2, and then this over 3, right, plus 5 over root 2, and then we don't have to apply the lower boundary because everything's just going to go to 0, which is why we chose to integrate it this way. So when we simplify this, let's see, when we simplify this, this gives us 2 pi. Actually, I'm going to factor out a 5 to make it easier. So that gives us 10 pi. And then when I factor out the 5, what I'm going to be left here is minus 2 over 2 root 2 divided by 3, right? So this is just minus, let's see, minus, I divide this by 5, minus 2 over 2 root 2 divided by 3, and then plus 1 over root 2. So then when I factor out the root 2 from the denominator, that gives us 10 pi over root 2. And then when I do this like so, it just gives us minus 1/3 plus 1, or 10 pi over root 2 times 2/3, which is equal to 20 pi over 3 root 2. And that's what we get for the volume.